Okay, so let's continue with our whirlwind tour of Python. I think I may have mentioned this IPython notebook. I don't think I actually showed you what it looks like last time. So this is sort of analogous to iStudio, to RStudio. And basically I opened this by just typing IPython space notebook at the command line. And it basically opens up this interface that's actually within a web browser that's just running on your local machine. So there's a whole bunch of functionality here, and this might be a nice way, if you're starting out with Python, this might be a nice way to play around with it as well. Okay, were there any questions from last time? So we left off, and we were starting to talk about different kinds of objects in Python, and we're going to do a little bit of comparison and contrasting with the objects that we're familiar with in R. And so we just saw lists in Python, which have a reasonable amount of similarity to lists in R. They can contain all sorts of heterogeneous information. And we also saw that, like when we worked with strings, there are all these object-oriented methods that we can use with a list object by just having the name of the list, dot, and then the particular method. So we saw that with this extend method. We saw it with sort, et cetera, et cetera. So that's kind of nice. Want to say a brief bit about indexing. We saw the range function last time. We figured out we could change it to be starting and ending at any given point that we were interested in. So I'm going to just create a list, 0 to 49. And then if we want to index into it, we have to remember that our indexing has to account for the fact that 0 is the start. And then the other aspect of it is that Python indexing works a little bit differently than R in that basically this says go up to the third element, but don't include it. So we get 0, 1, 2 back instead of 0, 1, 2, 3 back. So if you're switching over from R or going back and forth, you just sort of need to keep this in mind. One of the nice things about Python in comparison to R is we don't need to say what the beginning or ending index value is. We can just say go from 40 and go to the end, or go from the start and go up to 5. So that's nice. Usually in R we end up having to do 1 : length, and then we have to do a little bit more manipulations. And in Python we don't need to do that. So here that's going to take us from 40 to the end of the vector, and then this should just give us the first 4 or 5, I guess, of these as to sort of figure out the 0 and the ending index and all that. Okay. There are also these things in Python that are called tuples, which I don't know. I always think that's kind of a funny name. I'm not quite sure why. But the interesting thing about tuples is that they're lists it seems like each different languages have different sort of formal words for certain things. So in R people throw in the term lexical scoping for the kind of scoping that we've seen in R. In Python, people throw on the word mutable and immutable a lot, and that indicates whether or not you can change the values inside an object. So lists in Python are mutable. We can go in and just change any of the values in the list. But tuples are basically fixed once you create them. So you can't go in and change an element in a tuple. So this is handy in some cases where you want to be passing stuff around and having that be fixed and not have it be able to be modified. So it's sort of it's in some cases might be helpful for avoiding bugs in your code. So if we do type of data, it'll say this is a tuple. You might notice the only thing that's different from the way I defined this compared to the list was I used parentheses instead of the square brackets. So that's how we go about doing that. But other than that, it's holding the same sort of heterogeneous information that we had a list hold. And we can index into it in the same way as we did for a list. But if we try and change an element of it, it's going to say, oh, you can't do that. You can't modify an element in place in a tuple. However, you'll notice this tuple is made up of a number, a Boolean, a character string, a list, and then another tuple. So again, we've got all this nestedness. but we're going to see if we can modify the element of the list within the tuple, and that does allow us to do that. So it's a little more complicated. You sort of have to think through what's the different nestedness that I have in my object, and what are the types of the different pieces within the object. So I was able to modify. I guess this would be this. No, I guess that would be this element of this item within the tuple. But presumably I would not actually be able to totally replace this entire list with something else, because that would be at the level of trying to modify the tuple. This is at the level of modifying the list within the tuple, so I am allowed to do that. And then if I tried to modify the fourth piece, you would guess that I probably can't do that, because that was a tuple itself. So actually, let's see if I could just modify the third piece. Yeah, so that doesn't work. And then we can do the same sorts of things just to check that all the pieces of this guy are what we would expect. And it says, okay, yep, that's a tuple. Pieces of it are a list or an integer or a tuple, et cetera, et cetera. Okay, questions, comments? So another nice kind of object that exists in Python where there's not a direct analog to R, although you could make an environment, for example, behave like this, or you could sort of make a list in R behave like this as well, is what's called a dictionary. And this is basically a set of key value pairs. So there's basically a label or a key, and then you are able to look up the value associated with that label or key. So we'd probably run out of different types of symbols to start to indicate new objects. So maybe that's why these are the three main ones and there aren't anymore, because we run out of characters. But here what we're doing is saying, okay, in the lion label or the lion key, we're going to assign Simba. For the panda, we're going to assign none. So this is basically sort of missing value. Moby is the whale, and then here we're going to say there are three animals. So it's basically a structure that allows you to look up things by label in a really efficient manner. And I presume, although I forgot to check on this, that this is basically implemented using hashing. So if I then print this out, you can see it's indeed stored the elements. You can't rely on any ordering within these dictionaries, so you notice that it's sort of restored it in a different direction than different order than I had originally given it. And that's in part because we're supposed to be looking up these things up by name and not by index. And then if you want to pull out pieces of the dictionary, you can look up, so I looked up what the lion was. If I try and look up what the elephants is, there is nothing in there. So it gives me an error back and says, oh, there's an error in the key that you gave me, because I can't find that key in my dictionary. On the other hand, I can, I believe, assign in and create a new element of the dictionary. And now we've got elephants, and you'll notice that I can basically look up what I think are essentially arbitrary objects. So here I've assigned to the elephants key a list in this case instead of just a single item. And again, just like with some of these other objects, there are these object-oriented methods. So there's a keys method. I can, again, if I want to know what the, oops, I'm not in IPython. If I were in IPython, I could have just done the zoo dot and then hit tab to see what the different methods associated with a dictionary are. Okay, so let's now turn to looking at copying in Python and contrast that with what we saw with copying objects in R. So I'm going to just make a list, and then I'm going to assign that list to another object name. And then I'm going to change an element in the original object. So now if I look at data, that's now 0357, and if I look at my copy, that's also 0357. So that's quite different than what we saw in R. If you change an object and you've assigned, in particular a list, if you've assigned an element within the list after you've made the copy, basically both my copy and data are pointing to the same object. So this, again, there's sort of some nomenclature associated with this, which is this idea of shallow copies versus deep copies. So basically what we just did was a shallow copy in the sense of we just basically copied the name, and both of the names are pointing to the same thing. If we made a deep copy, that would actually be going in and explicitly in memory making a new object at a new point, a new position in memory, and then if you modify one, it's not going to have an effect on modifying the other. So if I can remember, how are we doing this in R? If we did .internal of inspect, we could get back the memory address of an object in R, and that would help us to understand copying and whatnot. So I can use the ID function in Python, and looks like it's not giving me back a base 16 number, but just a regular decimal number. It will show me that these two indeed are accessing the same object in memory. So you might then ask, well, how do I actually make an actual explicit deep copy? One way to do that would be to actually wrap this in a function called list. Since I'm not a Python expert, I would guess there are other ways to do this, but this is one way to do it. And now if we change data, we should see that the my static copy 0th element has not been changed, indicating that these are indeed different, accessing different objects. And we should be able to confirm that by looking at the ID and seeing that this ID is no longer the same as the ID was up here. Okay, any questions about that? So I want to say a little bit about functions in Python and scoping, which was obviously a topic we talked about a fair amount in the R context. So here's how you define a function in Python. You use this def keyword, and the syntax is sort of similar to what we've already seen with blocks of code, that we've got a colon when we begin one of these blocks, and then we do indentation, and then when we end the indentation, return back either having a new line or return back to the original level of indentation, then that indicates the end of the function. But other than that, a lot of, this doesn't look so dissimilar from our code. There's a return statement. There are some arguments. In this case, this is how Python sets up help information for a function. It's called a docstring. And so if I were to type help on this function after I define this function, I should get back this docstring. So basically, it's a nice mechanism whereby you can sort of, unlike in R, like in an R package, we haven't really talked about those, but in an R package you have to create a whole separate document. There are ways around this, but one way to do it in R is you create a whole separate help document for each of your functions. So you can do it, and it's quite nice when you do it, but it requires a little bit more rigor is not the word I'm looking for, but a little bit more discipline to do it. Here in Python, it's dead easy. You just type in the docstring here as you're creating your function, and then it all goes through. So I'm sort of forgetting where I'm going. Okay. I was having troubles when I was copying and pasting. Sometimes it worked in Python, and sometimes it worked in IPythons, and I've sort of forgotten which was giving me trouble and which was not in different cases. But if I now do help of my fun, indeed, it just gives me back that same information that I had put in. So that's all set up to work. So let's think about what happens when we modify objects within a function call. So basically, this is getting at this question that we've seen in R of passing by value and contrasting that with passing pointers, for example, when you're working in a compiled language like C or C++, whether you can modify an object that you pass into the function and not have to pass that object back out in order to have it take effect in your more general environment. So if we then go ahead and just run this function, I'm just going to set things up by defining my objects. I'm going to look at the IDs of those. And now I'm going to run my function. And you'll notice what happens in the function is I change an element of x to be 7, I change y to be 5, and I change z to be a new list. And so if I now run the function, then the other thing I've done here is I've printed out the IDs of the objects, and you'll notice a couple things. One is, so when I passed in X, Y, and Z, these are the addresses of those objects, or the labels of the sort of labels in memory of those objects: 440, 392, 520. And then right in the function, I did print the ID of X, Y, and Z. And so these are indeed the same IDs here. So it looks like Python, when it sets up the arguments to the function, it's just having the object names in the function just point to the same place as the objects were originally pointed to outside of the function. And then I modified X, Y, and Z, except for X, I just modified a piece of it, whereas for Y and Z, I basically made a new assignment to the entire object. And then I printed out the ID. I guess I should have decorated this with a little bit more information so it was easier to just read this off. But you'll notice this is the same ID as we originally had for X, even though I've modified the X, the 0th element of X. Whereas Y and Z have new IDs here. And then when I look at X after I've returned out of the function, X indeed is no longer, it started out as 075, it's now 775, so it's been changed in the global environment. But Y and Z are whatever they were originally, the 3 and then the 0 and 1, 0, 1, 2 is what I had set them up to be originally. So one way to think about what Python is doing is originally there was an X, a Y, and Z in the calling context, and those pointed to, I don't remember exactly what I had, but those pointed to something or another. Now I go into the function, and in the function I have these arguments X, this function, the signature of the function was X, Y, Z. So basically what's happening is in the function I'm setting up labels X, Y, and Z for objects, and they're basically pointing to the same things. Oops, sorry about that. Pointing to these original objects. So then when I come along and say, okay, X of 0 gets 7, well, okay, here's X. It points in here. It just goes in and changes that to a 7. It doesn't change the fact that this X on the outside in the calling environment is still pointing to that same object. But think about what happens when I say Y equals 5. Well, I'm basically just saying, okay, I'm going to do a new assignment of Y. So basically what happens is it just says, okay, you're assigning, basically sort of, if you read this off, it says, okay, take a 5 and assign it to Y. And so basically what's happening is it's sort of setting up 5 and then it's assigning there. And then the same thing with Z, because we're basically assigning a whole new object. It's basically now pointing to whatever the new thing that I created was. So if you do modify an object by modifying elements of the object, then in that case that's going to affect your calling environment. Okay, so any questions about that? Yeah. The original value of which? Well, these guys still exist in the calling environment, in the global environment. Right, so I might be misunderstanding your question, but when I ran my fun here, and then if I look at Y and Z, those still exist, and those are the original values that I had originally assigned to them. Okay. Other questions? Yeah, Dustin.
So if you do ID of X subsetted to the first element, then would that memory change? Would that address change?
No, presumably not, because this is presumably, I don't actually know exactly how lists are stored in memory in Python, but presumably what's going on is basically that there's some block of memory allocated for, well, I don't know, it might be more complicated than that, because we could modify this and have this be some huge other list in here. So I guess we'd have to go and we'd have to go and figure out how Python is storing stuff in memory. But if we, so let's do this again. X equals 0, 3, 5. I don't know what's going to happen if I do this. It's interesting. ID of x of 1. Okay, so is there any pattern to what I'm seeing here that would indicate there's anything contiguous about this? So the 0, 1, let's see, so x itself was 9, 1, 2, 3, 2, and then 0 goes up to 9, 4, 2, 8, and then 1 goes back to 9, 3, 9, 2, and then 9, 3, 6, 8. I don't know if these mean anything in terms of actual memory addresses, or whether they're just sort of abstract conceptual labels. So I guess then the question was, what if we run the function, right? So this should address the question at least partially, right? Okay, so now we wanted to do ID of x. Okay, so that's the 2, 3, 2, right? We knew that was going to be the case. But if we do it of 0, 9, 3, 4, 4, 9, 4, 2, 8. Okay, so it looks like that has changed. And if we did it of 1, 3, 9, 2, that looks like it's the same. So what Python might be doing, I'm just trying to infer this from what we've seen, is since each element of the list can be an arbitrary object, what Python might be doing is for each element of the list, it's basically pointing off to some other memory location where that component is stored. And so if you change the 0th element, I'm just guessing here. If anybody knows better than I do, let me know. But if we think about x, here's the 0th element of x, here's the first element. Basically what it might be doing is this might be pointing off to where the 0th element is actually stored. And that could be another list, some huge list. It could just be a number. This is pointing off to whatever is stored. Suppose that's a list. Suppose that's some sort of vector stored contiguously, assuming that we could create such an object, et cetera, et cetera. So I'm guessing this might be what's going on. Does anybody know better? Who knows Python better than I do? Or okay. So let's think about a little bit about scoping. Obviously, we covered this in R, and we saw that R looks in the enclosing environments and not in the calling environment. So I'm going to sort of just do essentially the same toy example that we did in R, and just try and empirically try and figure out what Python is doing. So here I'm going to define an x, and I'm going to have it use a. Of course, there's no a in my fun, so it has to go look for it. Presumably, it's just going to go look for it in this global environment. So that that addresses our question of whether or not it can find objects other than just in the scope of the function. It doesn't really tell us anything about what the rules are by which it's doing that. Since this myfun has the global environment both as the calling environment and as the environment in which it is defined. So let's do it now where we create two different functions, both within the global context, and then try and see where it's getting the a from. Okay, so it did 7 times 3, so it looks like, so what's happening here? If I did my fun of 7, I call here, a gets assigned to be 7, then I call my inner fun of x, so that's 7, I go in here 7 times, and if it looks for a in the calling function, it would get this a, and it would give 7 times 7, but what it must be doing is looking for a, presumably either, well, this still doesn't really address the question of whether it just by default looks in the global environment, or whether it looks in the enclosing environment, and the enclosing environment in this case is the global environment. So this tells us a little bit more about what it's doing, that it's not looking in the calling, in the context of the caller. So now I'm going to define a function within a function. So here I define my inner function within my fun, and then I'm going to call my inner fun here. And then the question is whether this is going to look for the a in my fun, which is the enclosing context for my inner function, whether it's going to look for it outside in the global. So it looks like it is indeed finding A within within my mon, so where it's defined. So looks like from this empirical investigation there might be more subtle distinctions, but if we delved into this more, but it looks like from this that basically it's doing something quite similar to the rules that R is using. And I forget if I had mentioned this, but I think in terms of sort of motivation for why this makes sense, at least within an R context, but it might extend to reasoning about Python, is if I forget if I've said this before, so forgive me if I'm repeating myself. Well, let's say I have the LM function, and that's defined in the stats package in R, and it has a bunch of arguments, and presumably what any sort of relatively sophisticated function in a package that does a bunch of stuff has to do a sort of complicated set of operations is going to do is there are going to be some helper or auxiliary functions in here that are sort of part of the LM or statistics functionality. So indeed, LM calls, for example, a model.matrix function. So maybe it might do something, that's an assignment, where it calls model.matrix, and then it goes on and continues its business. At this point, this LM would be called by you as the user in the global environment. And if the rule was to go look in where the function was called from, it would then go look for model.matrix in the global environment. And presumably, if R still had the whole search path set up, it could still go find model.matrix eventually in the stats package, which is where all of the stats and linear model stuff is defined. But it makes a lot more sense and is a lot more sort of coherent and packaged together if the rule is for it to go look for model.matrix in the context of where this is defined, because all of these functions that are being used for statistics and linear models are all sort of traveling together as a bundle. So I think that's part of the reasoning why that's the rule in R. That reasoning might sort of be similar reason to why Python behaves similarly. Questions? Okay, we can also look at how we can pass in arguments. So in R, we have a ton of flexibility of defining arguments either by position or by name of the argument, and in sort of mixing and matching things in lots of different crazy ways. Python is a little bit more structured in what you can do, but it has a fair bit of flexibility. So I'm going to define a function, mymult, that takes an argument with no default and then two arguments with defaults. And then actually return two values out of this, which is not something you can do in R. And what Python is going to do is basically package this up into a tuple. And then we're going to see whether Python is okay with us passing in the arguments in various ways. So if I pass in just a 5, presumably what's going to happen is it's going to use the defaults for y and z. And indeed, that's what it does. If I pass in a 5 and a 7, then if it's indeed using 7 and assigning that to y, then I should get 35 and then 5. So the x times y is the 5 times the 7, and then the z is just the default of being 5, and that's what I get here. And presumably this should also work. Here I'm just passing everything in by position ordering. Because I don't not quite need all this space here, so let me get these so we can see both of them at once. And I can do things like this. I believe this is going to work. So it does get y as the default, but then so you can basically skip one as long as the z is then given as a label so that it knows how to do the association. And you can pass in everything by name as well, so that works. And you can see it correctly did 7 times 3, so it is indeed doing the right thing there. But then my thought is, well, let me try passing in x and y by name and then relying on Python to realize that this is the third argument and that should get assigned to the z. And here Python's going to complain, and we'll see that it behaves a bit differently than R, which is in Python, all of the ones that are given by, you can't basically have the ones that are given by position be passed in after the ones that are given by name. And I think that's because Python is worried about sort of people getting confused about what arguments being assigned to what value. So it doesn't like this of trying to infer that this should be the z after having used the keyword or the name labels to start with. And then just so we can see that actually Python has somewhat more flexibility than R in terms of return values, I can do this nice trick, which is also the sort of thing you can do in MATLAB, so this is pretty nice. So I can assign into two different objects coming out of the function. As opposed to R, I'd have to pass a list back, and I'd have to unpackage the list if I wanted to get individual pieces out of it. So that, I like this because every so often in R that seems like a bit of a hassle, although it's not not a terrible thing. But I can also directly assign to a single object out3, and out3 is actually going to be a tuple, which is how the things are getting passed back. So I assume what's happening here behind the scenes is basically the result of this is getting passed back as a tuple, and then when the Python interpreter sees code like this, it says, oh, okay, there are two things in the tuple. You gave me two names. I'm going to do the assignment based on that. Something like that is presumably what's going on. I won't bother to run the type because we can be pretty sure this is a tuple by the fact that we've got parentheses around it when Python prints it out. Okay, so the last couple of things I want to show is a little bit of doing calculations and a little tiny bit of efficient calculation, and then we'll look at object-oriented programming in Python, and that will close off our quick tour. So I'm going to create a list that's, again, just the result of range, so this will just be 0 to 99. And then I'm going to do something called list comprehension. So this is a Python functionality for, in a fairly concise way, basically iterating through an object and doing some operations on an object and picking pieces out of being able to pick pieces out of an object. So it's sort of like, in some ways you could think of this as like doing an lapply or that sort of thing in R. So this is it's sort of like natural language, right? Like you sort of like read this off. But it has a structure to it, and we can interpret what's going on. So what this is basically doing is saying, iterating through data, and saying basically, as you move along through data, each element you're going to temporarily call num. And then we're going to return it back if that element is divisible by 2 or not divisible by 2 or, wait, what am I doing here? Right, not divisible by 2 or 3. So basically, this is only going to return back those elements that I've selected based on my condition here. And what I'm doing here, basically you can interpret the fact that there are these square brackets as I'm creating a list. And the fact that I have num here means that what's going to be put into this list that I'm creating is these num values, but only for this condition being satisfied. So basically what happens is I have a list, I iterate through, assign each of the things to num, check the condition, and if the condition is true, then I'm taking that piece and putting it into this list that I'm newly creating. So this is a way of doing subsetting based on conditions. And you guys know how you would do this in R. This is a different sort of functionality and way of doing it in Python. And so if we actually print this out, you can see it actually has done what I've asked to, which is just printing back the things that are not divisible by either 2 or 3. So you can do this in a lot of contexts, and you can do it in rather more complicated ways, and we can actually create more complicated structures than we did in that example with the 2 and 3 division. So this is I actually took this directly from the boot camp that I attended a couple years ago. So the guy who was running it is an astronomer, so this is a dictionary based on something about some sort of particles and the masses of particles. So if we look at this object, can you tell me what this object is and what it's composed of? Okay, so there's a dictionary aspect to it, but it's not just a dictionary. Okay, so it's a list of dictionaries. So we can tell it's a list because it's got we're putting it in square brackets, and then each of the pieces within the list is itself a dictionary where we've got, I guess in most or all of these cases, we have a 2-element dictionary. We've got 2 different key value pairs. So we could look at the type of that. That should tell us that indeed we were correct in our interpretation. And now I can do a little bit of list comprehension on that list of dictionaries. So here's my list comprehension. You can see it has a somewhat similar structure as we just saw in the simpler one. But take 20 seconds and try and look through this syntax and see if you can figure out what is going to be what kind of object is going to be returned by this list comprehension. All right, so anyone want to volunteer and tell me what they see here? Okay, so how do we know it's a list?
Square bracket.
Okay, so square brackets say we're basically creating a list based on whatever is being evaluated in here. And then how do you know that the tuples are the pieces of it?
And the round brackets around the.
Okay, so we're basically here, if we just had this code evaluated and there were an X that had these pieces to it, this would create a tuple just on the command line. So the fact that we've got square brackets for the list and then this within it says we're creating a list of tuples, individual tuples. So this is saying, okay, iterate over the items in particles, which is this list of dictionaries. So that would say each X is going to be one of these dictionaries. And then if the mass piece of it is less than 1,000, but less than or equal to 1,000, and bigger than or equal to 100, return that back. But what I'm putting into the list is not just the whole X. I'm actually structuring it as I'm taking the name of X and the mass of X and making a tuple on the fly and then filling in the list like that. So this is pretty nice. You can do some pretty powerful things with this. And if we look at the result, we should see that it is indeed what we just assessed there. So we have a list as being my mesons is the thing that was created. That's a list. But then each individual element of the list is one of these tuples. Okay, let's think a little bit about vectorized calculations. So if I take just range of 10, that gives me a list. We've seen that. And now I'm going to try and do a vectorized calculation. I think we might have seen this last time. And it didn't actually do the math that I wanted it to do, right? It took this, and it took the original 0 to 9 and concatenated it with itself, right? So it did sort of more like a string, in some sense, like a string kind of operation. So these lists are not really set up to do a lot of math that, in a sort of intuitive vectorized sort of way. And if I tried to do data times 3, anyone want to guess what this does? Say it again? Okay, so it's basically going to multiply data times 3, but it's not going to do it in a mathematical sense. It's going to do it in a sort of copying kind of sense. So if I do that, indeed, I get 0 to 9, 0 to 9, 0 to 9 3 times as a list. So that actually could be quite powerful for creating objects. We've used rep and seek in R, and this seems like it does something fairly similar. I realized as I was looking through this morning, I don't need that import here, so I'll just take that out. So actually, let's see how we can do vectorized calculations in Python. We're going to need to use NumPy, which is the package set up to actually do the numerical stuff. I assume that the reason for all this is because, unlike R, which was built by statisticians to do math and focus on quantitative stuff from the ground up, I suspect Python was built more to do string and operating system and other kinds of manipulations, and then the sort of more heavy-duty math functionality sort of got added on a little bit later. I don't totally know that that's the case, but that would be my guess. Which is not to say that Python doesn't do math well. With NumPy and SciPy and these other packages, it's actually very well equipped to do to do math. It's just a little bit more added on than maybe in the case of R or MATLAB. So I'm going to import the NumPy package. We have this ability to create a shortcut name, and I'm going to create one array, and I'm going to create another NumPy array by making random numbers. So now I have two different NumPy arrays. Oops. Vec1 and Vec2, you can see that they tell us that they're arrays. And now I should actually be able to do vectorized math on those guys. Okay. So it's not hard to do, we just need to use the right kind of object to be able to do it. And I can make matrices, which in NumPy, which in Python terminology, actually in C terminology for that matter as well, are called arrays. So here I've got I'm creating a matrix. That's a matrix where I've just basically filled it in as rows. So you can see it looks like the way sort of the way the syntax looks is like, oh, this is actually sort of looks like it's a list of row lists. But I can operate on them as a matrix, and I can do in terms of matrix sort of operations like transposing the matrix, or in terms of pulling out rows and columns. So here I'm pulling out the first two rows, and this is saying pull out all of the columns. So a little bit different than the R syntax, but same idea, and we know we can basically do all the same things, even if they look a little bit different. Okay, any questions about that? And we can do a little bit of exploration of some of the sorts of things that we did in R. So for example, I'm going to explore whether or not it makes sense to pre-allocate memory in Python in the same fashion as we saw with R. So here's what I'm going to do. I'm going to create a list, but the way I'm going to create that list is by sequentially adding pieces onto the list. So first I'm going to create a list that just has a single element. And then this is a list, not a NumPy array. So when I do plus, it's just going to do the concatenation kind of operation, not the actual math kind of plus. And we can time that. There's this time it package we can use. So if I do that, and now there's a time it function within the time it package, so I need to call that within that. And I assume the number is replicate the timing 10 times for this expression. You'll notice I defined the expression with these triple quotes. So it took about 2 seconds to create a not very large matrix. So that's interesting. It looks like it doesn't look like it actually assigned into X in the calling environment, which is sort of surprising to me. In any event, we can also time if we pre-allocate. So notice how I'm pre-allocating here. I'm using that star operator on an individual list element and doing it n times. As I said, since I'm not a Python expert, there might be a better way to do this, and there are presumably other ways to do this, but this does work. And then we could sequentially assign into the elements of x2 once x2 is already created. And like in R, we can see that this is orders of magnitude faster than if we continually sort of tack on to the object. And the reasoning is presumably the same, that when we keep tacking onto the object, we're having to create every single new object again as we're tacking things on. And that just takes a lot of time. And then I'll just show you a very quick example of using data frames in Python. So this is another add-on package as of a few years ago, but it now has a really extensive set of functionality for doing a lot of the sorts of things you would do with data frames and related operations that we know how to do in R. So there's this pandas package, and there's read underscore table function. You'll notice here in Python it's an underscore because this is not an object oriented method as it would be if there were a dot, whereas R just names it read.table even though it has nothing to do with object orientation. So this is basically going to operate in a very similar way to read.csv or read.table in R, and then we can do things like head and tail. We can look at individual observations. You'll notice here there's only one set of indexing, so this is just by default indexing rows. and we can pull out individual columns in a similar sort of way as we did in R. And part of the reason this is similar is because the developers of pandas were basically working off of R, knowing that lots of people liked the data frame functionality. So I wonder if I'm just not in the right working directory. I'm not? Okay, so how do I get there? Anybody know? Oh, that's a good idea. I wonder if, I don't know if that will work as like a command. No? Okay. Like this? Okay, so this is going to be in, what did I do here? I have the double dots, so I'm doing relative. Okay, so let me go burrow further in. Does that work? No such file or directory. It's funny because I did tab completion to get there, so you'd think it would exist. All right, I'm going to do the quick and dirty way. No module. Oh, I guess I don't have pandas on this particular machine. Okay, so I think I will just have you trust me that this works, and if you wanna run it, open up one of the SCF machines, and this will actually run. But it, basically it's meant to mimic R, and it does do essentially what you would expect. So, say briefly give an introduction to the object-oriented stuff, and then we'll finish that off on Monday. So basically, a lot of Python is built around object-oriented manipulations, which we've already seen. And the sort of basic syntax for what you do in Python is you define a class with a particular name. You can have inheritance, just like we saw in R with LM and GLM and those different kinds of inheritance. You can have these base classes that your class inherits from. Again, you can have a documentation string for your class. And then you can actually insert some code here that will execute whenever you initiate a new object in this class. So we'll see an example of what you might do there. You can also have variables that are part of the class as opposed to variables that are actually part of an object within the class. So you can basically carry around sort of global information associated with the class by defining variables here at this sort of top level of the class. So that's something that I don't think you can do in R. In fact, I'm fairly sure you can't. And then we can define the methods for the class here using just basic function definitions. So I think I will quit there, and we'll finish. So we'll finish this. This will just take a few minutes to finish off on Monday, and then we'll launch into the parallel processing unit. Hold on one second.